We will continue with the outer solar system with Samathan Lawler, pardon me, is going to talk about more about the classy discoveries in the distant outer solar system.
Hi, everybody. I am Sam Lawler. I'm along with Wes Fraser, the other co-PI of the Classy survey. And I have to start with a little bit of hearts and puppy dogs and baby goats and just say thank you. I'm so grateful to be here today. I'm grateful to be visiting from Treaty 4 land where I live and enjoy the beautiful prairie skies. I'm grateful that you also have online participation because usually that's where I am. I don't travel much anymore. And I wanted to say thank you for doing such a great job with this telescope. It's been amazing. Classy, let's talk about the science. So Wes gave us kind of the background on the Classy survey. Just a reminder that our two main science goals are to get the size distribution of very small TNOs. Justine Obadowski is going to be talking about this tomorrow. We're looking at the second main science goal is to look at the orbital distributions of the most distant TNOs. And I'll be talking about that a lot. And some bonus science cases. So, one of the bonus science is, so the way that we're taking our data, we're getting lots of 5-minute exposures and shifting and stacking them. But for the brighter TNOs, that means we have many observations over the course of a few hours, and we can get light curves. So this tells us about the shape of these TNOs, right? Are all of these weird snowman pancakes like Erikov? That's the kind of question that we will start to be able to answer. We also we found the midplane of this part of the Kuiper Belt. We wanted to focus on the most dynamically cold, the densest part of the Kuiper Belt. And so when you look at the sky, there's the ecliptic plane, right? Earth's orbit projected outward. There's the invariable plane, which is, the average plane of the solar system, mostly Jupiter. And then there's the forced plane, because out in the Kuiper Belt, there's, gravitational interactions with Neptune that kind of warp it a bit. So we tried to aim for the forced plane. And the way that we know we got it is a plot like this. So this is a polar plot showing inclination and longitude of ascending node, a polar plot. So for comparison, so this is what we saw with OSIS. So OSIS was not trying to get right in this midplane. So you can see these lines through this inclination node space are kind of all over the place, right? But with Classy, there's a nice bullseye. We got it. So Yukun Huang did the calculations for this. We got the most dynamically cold Kuiper Belt objects that we could. This is exactly what we want for probing the size distribution and learning about the primordial planet formation process. Okay, so let's talk about orbits. This is our second main science case for Classy. We already know that resonances are very, very important in the distant solar system. This plot is showing some of the results from OSIS, where we have, because it's well characterized, we know the absolute populations in these different resonances. We know there's lots of stuff in resonances. So let's go a little bit deeper and see what we learn. But first I have to tell you a story. So everybody has seen this plot. Does this look familiar? So this is what spurred the Planet 9 theory, right? So these very distant TNOs with fairly high paracenters. The first few that were discovered were all on one side of the solar system, right? And one way you can explain that is if there's another planet out there, this 10 Earth mass, hypothesized, very distant Planet 9, right? So this is the data from 2016. I'm going to rotate this so that it matches my plot that you're going to see next. And so now when we add in all of the very distant TNOs that have been discovered since then, it looks like this. So there's definitely still an asymmetry, but that very strong clustering is not visible in the data anymore. But not all of these TNOs are equivalent, right? There's a lot going on out here. So a recent paper looked at, so this is showing semi-major axis along the bottom and pericenter distance on the y-axis. And so as you go to larger and larger orbits, it takes smaller and smaller energy kicks to change the orbits, right? So you can see there's this diagonal green line. Everything gets there's a limit, a stability limit. You can argue this, right? So they've said, okay, so some of these are more stable. So what does that look like when we take just the most stable ones? Oh, look, the clustering comes back. Except when you look more carefully at these ones that are left, so Kat and Volk recently did an analysis and found that actually almost all of these that are left are resonant with Neptune, which means that they are confined, but they are confined by known dynamics. You don't need anything extra to explain them. So, okay, so let's look at this a different way. So here is, again, along the bottom, semi-major axis versus pericenter distance. So Neptune would be like way off in the lower left corner of this plot. So this is what we knew in 2019. We've added a couple more in the last couple of years. We can actually explain everything on this plot with known solar system dynamics without adding anything extra, except for those guys. Those three objects, we can't explain them. Like, how did they get onto those orbits? Those are the really interesting ones. So let's find more, and that's what we've tried to do with Classy. So here's that same plot again. So now the pink ones are those three, right? And they're kind of all over the place. And that's what we did with Classy. We looked all over the place. Let's find very distant Kuiper belt objects in several different directions, right? And so we're still in the very preliminary stages of this. We actually got a lot, like our main survey is done, but we're still getting a trickle of data. We actually got data last night. Thank you. So here's a preliminary plot. Our orbits are still pretty uncertain in semi-major axis and eccentricity, but the distances at detection are very well measured. Thank you, Brett. So this plot is showing where are these TNOs that we've discovered, and we kind of expected to see more out at 60, 70 AU, right? That's the really interesting part. Those are the really distant ones, and there's not much out there, right? So what does that mean? Does that mean there's a different size distribution out there? Does that mean there's a different inclination distribution? This is where we are now. There's a lot of very cool science that's going to come out of this plot. And I'll note that LSST is not going to help significantly with this, right? The magnitude limits are just too shallow. We really do need targeted deep surveys to find these most distant objects. So stay tuned. A few other interesting discoveries to highlight, because we're looking at this very low inclination part of the soul. Well, we can find higher inclination stuff, but we're mostly finding very low inclination things there. So this is showing the 5-2 resonance, everything that's known. There's this new guy down here that is it in the resonance that's got very uncertain orbit right now. Here's another way of looking at the orbital uncertainty. It has, so the black dots are possible orbits that it could have within our uncertainties. The lovely rug pattern circles are where it needs to be in order to be in this resonance. So it's probably not in the resonance, but even if it's not, that's also interesting. That tells us it dropped out of the resonance while it was migrating. That's telling us about the size distribution of planetesimals that Neptune was scattering, right? There's a lot of good science here, no matter what falls out of this orbit. One reason that we don't have a lot of resonant objects yet is because it takes very high orbital precision, right? So we have to get down into this very bottom part of the plot, which takes a few years of tracking. So we will be following up our most promising candidates with various telescopes, hopefully CFHT, and getting better orbits. I just want to talk about one one more interesting one that we discovered with the LIDO survey, part of the OSIS family of surveys. This survey looked at higher inclinations. We discovered a huge fraction of resonant TNOs, including this 10-to-1 resonator. This is the first secure one. And we had to get down to incredibly high orbital precision in order to have it fit inside that phase space to be definitely in the 10-to-1 resonance. So we actually had to do Gemini follow-up to our CFHT discovery data and go back and get some Subaru archival data. Thanks CADC for making that easy to do. So this is really interesting, right? This goes around the sun once in 10 Neptune orbits, right? And it's securely tied to Neptune's orbit, which is very cool. So kind of our early takeaways are resonance, just reinforces resonances are super important for the distant TNO populations. Finding more distant objects with really good orbits, that's the key to understanding the past of our solar system's formation and the current dynamics. What else is out there that we haven't found? And CFHTQ observing has been absolutely vital to this. Thank you so much. But I have to end on a really depressing note because our data is getting more and more compromised. There are almost 8,000 Starlink satellites in orbit now, up to 1 million planned by many different companies. So Jack Patterson has a talk tomorrow talking about how satellites have affected our survey. But we're at the point now where even if you're doing spectroscopy, you've got a good chance of having a Starlink satellite fly through and add a solar spectrum to your data. So there's a lot of satellites. The light pollution makes me very sad. The pieces of SpaceX spacecraft that have fallen near my house make me very worried. The possibilities for collisions in orbit make me feel kind of ill. And the atmospheric pollution from the disposal of all these satellites is what keeps me up at night. Right, we're already at 2 or 3 Starlink satellites burning up in the atmosphere per day. We're above natural infall rates of metals. The atmospheric composition is changing because of these satellites. Everyone here in this room and online, we are well poised to fight this, right? We're kind of the canaries in the coal mine for this environmental disaster that's happening in orbit. Please come talk to me about ways that we can work together and try to save the night sky. So thank you, everyone.
Very much, and thank you for that important reminder. At Vansar, we do save all our satellites, particularly the highlighting. There is a little light pollution problem and atmospheric pollution problem. Okay, questions?
Thank you. Very nice. You were summary that work out the that appears to get the outbase and so very again.
Yeah. So the question was the uncertainties on the orbit in order to diagnose resonance. Is that So this plot shows. So we really get for this 10-to-1, for example, we really had to get down to this like 10 to the -4 limit in semi-major axis. Semi-major axis uncertainty divided by semi-major axis is how we measure it. So we really had to get way down here, which you can see for OSIS took a very long time. So we will need years long follow-up and going back and finding archival data to get this for Classy. But I'm hopeful that we can do it for at least a few really interesting ones.
Thank you very much.